All right, so section 11.6. So we're going to talk about a couple different kinds of surfaces in space. So we've talked about vectors in space. So now we're going to make things more interesting and start talking about surfaces. And kind of from here on out, it's important to remember when we're looking at equations, when we're looking at these things that we write down, that we are talking about 3 dimensions. It's easy to get stuck in the plane and think, oh, I know what this is. This is a particular kind of shape. Well, we want to think in 3D now. So we've already talked about a couple of kinds of surfaces. We mentioned kind of briefly, and something that we're a little more familiar with, spheres. Spheres are pretty nice surfaces in space. And our equation for a sphere in space is just an extension of the equation for a circle in the plane. So I'm just going to write this down. We're not going to do a lot with it. There's some questions. You'll be working with it a little bit, but this is not really anything amazingly new. So there's our equation for a sphere in space, and our center is x0, y0, z0, and a radius is r. And this follows along from the distance formula, really, in 3 dimensions, the Pythagorean theorem in 3 dimensions. That's where these terms come from. So sphere in space, distance formula in space, just an extension of circles and distance in the plane. We also did a little bit of work with planes. That's another kind of surface in space. So just let's write down an equation for a plane in space. So there's an equation for a plane in space. And our normal vector is the vector ABC, and our point on the plane is x1, y1, z1. I guess we could have used x0, y0, z0 also. So that's the second kind of surface that we've talked about. So we're working on getting some familiarity with plane. What we want to talk about today is cylindrical surfaces and quadric surfaces. So just again, kind of an extension of what we know, but we're moving it into 3 dimensions. So let's look at cylindrical surfaces. And when we're talking about cylindrical surfaces, we're kind of expanding our definition of a cylinder. What we think of as a cylinder is kind of a special case of a cylinder. So a cylindrical surface is an equation that's going to involve 2 of our 3 variables. And when we graph the equation in one of the coordinate planes, we get what we call a generating curve. And the easy mistake to make with cylindrical surfaces is to look at the equation and think the generating curve is the surface. So we're thinking in the plane. So when we're looking at these, we want to think about 3 dimensions again. And again, it's not necessarily a cylinder in the way that we think of it. A cylinder from geometry would be a cylindrical surface with a circle being the generating curve in the plane. So a regular cylinder intersects a coordinate plane in a circle. So the circle would be a generating curve, and then we extend that 3 dimensions and we get a cylinder. We do the same thing with these other cylindrical surfaces. We figure out what their generating curve is, and then we can stretch them out into the other dimension. So what I want to do is just look at a couple examples of cylindrical surfaces and how we go about sketching them. So if we have z equals y squared, and we want to sketch this, and we can often you'll be asked to classify these also, and the classifications are not kind of set in stone. So z equals y squared. So let's sketch our axes. So z equals y squared, what's going to be our generating curve? It's a parabola. So our generating curve is a parabola in the yz plane. So if I sketch this parabola in the yz plane, I'll do this in red. Let me extend my y-axis back this way also. So if I sketch a parabola in the yz plane, we don't have to make it a perfect sketch, but a parabola in the yz plane would look something like this. So that's z equals y squared. So that's our generating curve. Well, for this curve, x can take on any value. Z equals y squared for any value of x. So I could graph the same parabola for any value of x. So what I end up with is I'm going to sketch a little parabola out here as well. And then we connect these parabolas like so. And this could also extend back into the negative x direction also. So what this surface is, what this cylindrical surface is kind of a trough shape. X can take on any value, z equals y squared for any of those x values. So we get this trough that's cylindrically shaped. So if we wanted to classify this, we could call this a parabolic cylinder. So it's this parabolic trough that extends along the x-axis. So this would be an example of a cylindrical surface. Our equation only involves 2 of the coordinates, and our third coordinate can take on any value, and that equation is going to be true for any of those values of the third coordinate. Does that make sense? Let's look at one that's a little more interesting, but the same kind of idea. So we want to sketch and classify z equals sine x. So our generating curve is going to be a sine curve in the xz plane. So we'll sketch our generating curve and then come up with our surface. So our sine curve is going to be in the xz plane here. Let me sketch that. I'll do it in blue this time. So we're in the xz plane, and my curve is going to look something like that in the xz plane. And y can take on any value. So I would get these sine curves for any value of y. So over here, I'd get another one. And along here, I'm going in the positive y direction only this time. Like so. And then we connect these. There's where it goes through the xy plane. So our surface would be this kind of sinusoidal shaped sheet. I think of it as kind of a corrugated, like a corrugated tin roof. Just keeps going, undulating like that. So this would be kind of a sinusoidal sheet. And when we classify this would be a sinusoidal cylinder. So z equals sine of x for any value of y. So this is going to extend along the y-axis and be this sheet. And in your homework, what the homework is doing, really, this first little bit of the homework is just trying to get you, give you a little bit of practice visualizing these kinds of surfaces. It seems kind of strange to call a shape or a surface like that a cylinder. And that's how we define a cylinder in space. All right, questions on those surfaces? So these, especially the cylindrical surfaces, it's easy when we're working in 3 dimensions to say, oh, this is just a sine curve in the xz plane, and then be done. We want to remember that we have our 3rd dimension that we're dealing with as well. All right, let's talk about our 4th basic surface. So a sphere, plane, cylindrical surface. Now we want to talk about quadric surfaces. Our quadric surfaces are going to be an equation, a 2nd degree equation that involves all 3 variables in some way. And the intersection of the surface with a particular plane, usually we talk about the coordinate planes. The intersection of a surface with a plane is called the trace of the surface. The trace of quadric surfaces are conic sections. All right, and does anyone have their book handy here? I forgot to grab mine. I just want to look. I have a page number written down, but it's from the previous version. You have one? I just need to look at the page. So the book has a nice table listing out quadric surfaces, and I'm not a big one for memorizing the forms of the equations, but there's a nice table on page 796 and 797. Has a table with quadric surfaces and their standard forms of their equations. So you don't need to memorize these standard forms. It's good to be familiar with them. What I suggest in the way I look at quadric surfaces is more being familiar with what their trace is in the coordinate planes, and then sketching the surface from there. So we need to be familiar with our conic sections, so we can look at our traces in the coordinate planes. So I want to look at just one example of a quadric surface, and then kind of turn you guys loose on some of these, practicing with some of these. So we want to sketch and classify. X minus y squared plus 4z squared equals 0. So second degree equation involves all three of our variables in some way. So we want to sketch this and kind of give it a name. So let's look at our trace in each of the coordinate planes. I'm going to rewrite this because x isn't squared. I'm going to rewrite this as, and let's see, I want to change this. I want this to be a minus. That'll make our surface a little nicer. So I'm going to rewrite this x equals y squared plus 4z squared. And then we're going to look at our trace in each of the coordinate planes. So in the xy plane, z equals 0. Our trace in the xy plane is x equals y squared. So what's that trace? Parabola. So we'll have a parabola in the xy plane. In the xz plane, y equals 0. We have x equals 4z squared. So another parabola, just a little different shape. And then for x equals a constant, so parallel to the xy or yz plane, because if we just set x equal to 0, what do we get? If y squared plus 4z squared has to equal 0, we just get a point. So in the yz plane we have a point, but we can talk about parallel to the yz plane. and we're going to say x equals a constant, we get y squared plus 4z squared equals a constant. So what kind of shape is that? That's going to be an ellipse. So in the xy plane we get a parabola, in the xz plane we get a parabola, and parallel to the yz plane, for x equals a constant, we get an ellipse. So let's try to sketch this thing. So there's z, y, and x. So in the xy plane, we have the parabola x equals y squared. So I'm looking in the xy plane. Here's our, we do this in red. And I'll do it in the negative direction. So this is in the xy plane. There's my parabola in the xy plane. In the xz plane, I get another parabola. So I'm going to do that in blue. This can get kind of messy here, but in the xz plane we get a parabola in this plane, like so, and down below, like so. So we get these parabolas opening up along the x-axis. And then parallel to the yz plane, parallel to this plane, we have ellipses. So we're connecting these parabolas with ellipses. So I'm just drawing my connections in like so in black dots. So we end up with a parabolic shape, kind of opening up along the x-axis. It's bigger it opens wider in the xz plane than in the xy plane. So we get this kind of parabolic shape that opens up along the x-axis. So this is called a elliptical, because we have these ellipses, paraboloid. So we call it the paraboloid because of the parabolas. We call it the elliptical paraboloid because of the ellipses. One way to visualize this is if I have a flashlight here. If you think of the shape of the reflector of the flashlight, that's an elliptical, or this would be a circular paraboloid. So the reflector of the flashlight is a parabolic shape that opens out. So if this reflector just extended out and out and out, really big reflector, that would be what this shape looks like. This would be that reflector of a flashlight. So that's an example of a paraboloid. So with the quadric surfaces, what I suggest is you sketch their trace in the coordinate axes, and then we connect those traces based on what the information tells us. And I would recommend that you look over that table in your book that gives the general equations of these quadric surfaces, but it's going to be more beneficial for you to be able to see what the traces are in the coordinate planes and work with them from there rather than memorizing their forms. And we're just starting with this. By the end of the year, we will, as soon as you would see this equation, you would be able to hopefully be able to visualize this surface. We're going to work with these surfaces quite a bit, and we're going to work on visualizing these surfaces a lot over the course of the next towards the end of the semester, and next semester we'll work with them quite a bit, so that we, by the end of the year, you should be pretty good at visualizing what these surfaces look like just by looking at their equation. You'll have an idea of what it looks like. It's kind of fun to be able to see that in your mind. What's that? My definition of fun? Yeah. So this is like the Tranya that I mentioned earlier. The vectors, I said Tranya. I hope you enjoy the Tranya as much as I do. Surfaces, three-dimensional surfaces are kind of tied in with that. Are you guys? Did I ask you about that? Any old school Star Trek fans? I'll have to show you the episode that talks about Tranya, because I always, when I think of vectors and I think of surfaces, that I always hope that the students enjoy them as much as I do, but we start out kind of not really sure that we're going to. All right. Homework today.
One screw and fix oh my God. I don't know if that's actually true, but I want to be best.
All right, there you go.